Hello everyone, welcome to the lecture series on IC applications. Myself Siva Ramakrishna, Assistant Professor in Department of ECE. In this lecture, we are going to continue the discussion on data converters. In the last lecture, we have seen the introduction. We have given introduction to the data converters. What is the need for data converters and what are different types of data converters. So we said there are two types, nothing but digital to analog converter and analog to digital converter. And we have before discussing the types of data converters. That means that these data converters are classified into two types basically. So what are they? One is DAC, so which performs conversion of digital data to analog data, and another is nothing but ADC, so which converts data from analog form to digital form. We have seen the reasons and need why we need to perform data conversion in real-time world, in real-world applications. What is the necessity? So this we have illustrated with respect to an example, saying the plant, so which is going to generate some analog signal initially, so that we are going to capture with the help of a transducer, because voice signal is a non-electric signal. We need to convert that into electric signal, so that we are going to use a transducer, and then we have used this filters, nothing but anti-aliasing filters. And since the obtained voice data, which is definitely in analog form, is not clear, it requires a kind of processing. We need to process this voice signal. For instance, for example, we need to process this voice data to use this as an end application in order to get, in order to obtain a clear and improved or quality voice signal. We need to process it. Since processing of this analog signal is quite tedious, it requires several and multiple number of applications, and even the hardware requirement or software requirements are going to be very challenging if we want to process the analog signal. So we are going to convert this analog signal into digital signal with the help of an interface or with the help of a converter called analog to digital converter. The output of this block is said to be pure digital data, which consists of zeros and ones. Now the data is in the form of binary values, nothing but zeros and ones. So this data can be used to process. So this digital data is applied as input to any system having a dedicated software, which will effectively process this voice data to improve the quality. Or the straightforward thing is nothing but a digital signal processor. No need to be a voice signal. It can be an image, it can be a video. So we want to process this. Why we need to process? To improve the quality. I want to improve the quality of the data, so that we are going to process this with the help of a software, with the help of a PC or any computer having a dedicated software, or we can use any digital signal processors. And now the output of this processor is going to be again a pure digital, because we are going to perform some operation, or we are going to operate the digital data, and the end output of this plant is going to be digital data. Now who are going to access this digital data? Finally, we humans are the end users of this data. No one can understand this digital data. It is hard to understand the digital data, which is in the form of pure ones and zeros. Now the data, the processed data, is in the form of ones and zeros. So what we need to do? The end users are going to be humans. So once again we need to convert this data back to the original form. What is the original form? Analog. So here we are going to introduce the interface called digital to analog converter will produce an analog output. which is fairly or closely matched with the original input. In order to smoothen, in order to replicate, in order to get the exact original signal, by removing any unwanted frequency components or any other nuisance components, we are going to use the smoothing filter. The output of this digital to analog converter is applied as input to the smoothing filter, will smooth the signal, will smooth the obtained digital signal from DAC, and will remove any additional or unwanted nuisance components which are not present in the original input. So again the signal is sent back to the plant. So where we are going to get the improved signal. It may be an image or signal or improved version of the original data. So this is an illustration where we are going to use, where the two techniques will fit simultaneously. So in both the ends, so we said this can be a transmitter end, this process can be called as a transmitter end, and this can be understood as a receiver end. We need both digital to analog converter as well as analog to digital converters, depending on the applications or depending on the platform, right? And we have seen what are various types of ADC. So not the types. So what is ADC? ADC is an interface or any electronic circuit which will convert the analog signal to digital. The analog signal to digital are known as analog to digital converters, and the signals, the circuit are an interface that converts digital data to analog, called digital to analog converters. And with respect to the data, so what is the quantity of the data, and what are different types of data? We can classify this data fairly into two types. So the data can be classified fairly into two types. They can be a pure digital or they can be a pure analog signal. So we have described the basic characteristics of these two data types. So what is meant by digital data? So this can be considered as a digital data. So where we can experience discrete, there will be nothing like a continuous. There will be nothing like a continuous, and the quantities present in it are evenly spaced. They are distributed evenly, and in all the aspects, it may be the time or magnitude, they appear in the form of they never be a continuous. The parameters that describes the nature of the signal are not going to be continuous in nature. We can say that they are in discrete in nature. And then what are the analog data, which is well-known data and which is abundant in nature. For example, we can say the voice signal. Again, it is nothing but a analog data. We will have all the parameters, whether it is an amplitude or time, they are in continuous values. The range of all these values are going to be continuous in nature, both in temporally as well as in terms of the magnitude. We can express this analog signal in continuous in nature. And then, so we define what are the data converters available. Since the targeted data are going to be only two types. What are they? The data can be either digital or analog. The data can be in the form of an analog form, or it can be in a digital form. Right. So depending on the application and depending on the processing, depending on the purpose, we need to convert them. So according to that, we have two types of data converters. What are they? They are going to be analog to digital converters, and the second one is going to be the digital to analog converters. Now coming to the discussion, what are different types of data converters? The objective is to convert data in one form to another form. So we have fairly two types of data. The data are broadly classified into two types here. So what are the analog, or it can be a digital. Now what is ADC or DAC? Are nothing but an interface. As we said, these are the circuits. These are also considered as a circuits. We can call it as an electronic circuit, right? So now we are going to design the converters. We are going to design the converters using operational amplifier. Here comes the IC called as operational amplifier. With the help of op amp, we are going to design the two converters, namely, so what are the DAC? We are going to DAC. Also, we are going to design ADC with the help of an op amp. Understand? Now, before we discuss ADC, we are going to discuss DAC. So, what is the reason here? While designing ADC, while designing analog to digital converters, we use the services of DAC. There will be a block. So if we say this is, if we say ADC, we are going to use the services of DAC. That is, it will play an intermediate role to get the final output from the ADC. Right. So now let us look at the digital to analog converters. So what are digital to analog converters? So this is the hierarchy of the discussion. So what are the key points here? We are going to design electronic circuits for DAC as well as DAC with the help of operational amplifier. So first we are going to discuss digital to analog converters. So what are digital to analog converters? They convert the data. So the data fairly in the form of binary. So this is the initial form of the data. With the help of this interface or electronic circuit, we are going to obtain the final output, which is going to be in analog in nature, right? And also we have seen the applications where we use this DAC and ADC, right? There are numerous amount of applications for both DAC as well as DAC. Most of the applications do exist in communication and signal processing techniques, right? Now in this lecture, we are going to focus on digital to analog converters. So what are digital to analog converters? So it is an electronic circuit that converts a digital input to analog output signal, and the digital signal which is considered here is represented as a binary code. That means the data which we are going to use as input will be in the form of binary 1 or it can be binary 0, right? Or it can be a combination of both bits, zeros and ones. So that is the data we are going to use to perform DAC operation. Now let us look at this one. The number of binary inputs considered as a single output. So in general, what is the nature of the data? Digital data, how it will appear? It will appear as a sequence of data. It can be a 2-bit data. The digital data appear here. In general, it can be a 2-bit data, or it can be a 3-bit or 4-bit, or it can be an 8-bit data. So that means we are going to consider the entire sequence of the data. It can be 1 0. If you say it is a 3-bit data, for example, we can say 110. Any data. That means if you say it is, the data is going to be a 4-bit data. So this complete data is considered to generate the analog output. So this one, if you say this is going to perform a 2-bit DAC. If you want to design a 2-bit DAC, we are going to consider the 2 bits. If it is a 3-bit data, in a given time we are going to consider 3 bits. If it is a 4-bit data, we are going to consider the 4 bits which are coming as input to the DAC to generate the corresponding analog output. The output is going to be a pure analog output, right? And now let us look at the basic functional block diagram. Let us look at the basic functional block diagram of the digital to analog converter. So here we can see this is my input, and in the output I am going to get an analog signal, let us say some volts, right? Since it is going to be expressed, the analog signal is going to be expressed in terms of some certain magnitude or some volts. So what is the magnitude of the signal for the input data 10? Will cause let us say 2 volts. It can be, for example, I am telling, if you see we are designing a 3-bit data. So what is the output voltage for this 3-bit data 110? So in a given time we are going to process the 3 bits if it is a 3-bit DAC, or we can process the complete 2 bits if it is a 2-bit data, right? And according to the data obtained, according to the input data, we are going to generate the output voltage, will be in the form of volts. So that's what we are going to say. So what it is, we are going to take the digital data, which will be in the form of binary, and the general representation, if you say any digital data will have LSB, there will be LSB and MSB. What is meant by LSB? Since the digital data considered here is a sequential form, it is nothing but a sequential data, will have sequence of numbers, either zeros or ones. So if I say 4-bit data, let us say 1001, here I need to specify the LSB as well as MSB. So for instance, this I am going to represent as an LSB, and this I am going to represent as MSB. What is meant by LSB? LSB is nothing but the least significant bit out of the data represented. For the given data, this we will consider as the least significant bit, and this will be considered as the most significant bit. So which is the last bit, which is the last digit or binary data obtained for a given sequential data, right? So we need to specify the LSB as well as the MSB. So here we are going to say this is an n-bit operation where the first binary bit is represented as, it can be a DN, and the last bit is represented by D1. This is my last or the final digital data, and this is my initial digital data, so which is represented as an LSB, and here I am going to represent this as an MSB. No need to be the similar form, we can interchange, we can say DN as an MSB or D1 can be an LSB, but the things should be very clear, which bit is going to be the first bit, which is going to be the final bit, right? And the another important parameter considered here is going to be the reference voltage. We are going to consider the another input to this functional block diagram is nothing but a reference voltage. Right now here we have two inputs. What are they? One is the digital data. This is the digital data, and the other one is going to be the reference voltage. It can be minus 5 volts or minus 10 volts, that we need to set in the very beginning of the circuit design, and the output is going to be the volts, right? So this is the simple functional block diagram of a DAC. So here we are going to operate with n number of bits. So we can design a bit. It can be a 2-bit DAC, 3-bit DAC, 4-bit or 8-bit DAC, right? Now, what are different types of DAC with respect to an operational amplifier? Now, the entire discussion is going to focus on designing DACs are DAC, digital to analog converters, in the context of operational amplifier. These are classified into 3 types. We have 3 number of types for DACs using op-amp. So using op-amp, right, there are 3 types. The first one is going to be the weighted resistor type DAC, and the second one is going to be the R2R ladder DAC. The third one is going to be the inverted R2R ladder DAC. So these are the 3 techniques that are available to perform digital to analog conversion using operational amplifier, right? So each method has their own advantages and disadvantages. So as we proceed in the lecture, you will come to know the design, how to design, and we are going to perform some analysis, nothing but the design analysis, and then we are going to discuss the disadvantages as well as advantages of each technique. Since we define multiple techniques to perform digital to analog conversion, so we need to describe what are the drawbacks or what are the advantages. We need to describe the advantages and drawbacks of each technique. In this lecture, we are going to focus on designing or the discussion is a weighted resistor DAC. So let us look at this diagram. Here we can see this is an op amp. So which is operated in the inverting mode. It is operated in the inverting mode, and non-inverting terminal is connected to the ground, and this is nothing but a feedback resistance, and finally this is my output, right? And this is nothing but a weighted resistor network. So here if you observe, we have number of switches are nothing but digital switches. These are all nothing but the digital switches. The switch will toggle between two positions. So what are the two positions? The switch will will be connected to the reference voltage VR, or it can be connected to a ground. It purely depends on the incoming bit. Suppose if the data is 0, if the incoming bit is 0, then the switch will be connected to the ground. If the incoming bit is binary 1, then the switch will be connected to the reference voltage. So this is for n-bit DAC. Now let us describe this operation design this circuit with respect to the 3-bit. So how to design a 3-bit circuit now? Let us consider this. I am going to have an op amp. This is my operational amplifier. I am going to operate this in the inverting mode. So which means the non-inverting terminal is connected to the ground, right? And inverting terminal. So what we are going to have in the inverting terminal? We are going to have weighted resistors. We are going to have a set of weighted resistors. Do remember, the LSB is going to possess the highest resistance, and as the number of bits progress towards the MSB, the weight of the resistor is going to decrease, and finally the resistance value of the MSB is going to be very minimal. So let us connect that. I am going to build a weighted resistor network. Since I am operating with 3 bits, so I need to consider 3 resistors. I need to have 3 resistors, right? And these resistors are connected to 2 positions. What are the 2 positions? They can be connected to either a reference voltage. Let us say this is my reference voltage. Here I am using minus VR. Since the operating mode of this operational amplifier is in the inverting mode, my reference voltage in the design is going to be the minus VR. So these are the positions we are going to describe or define. So these are nothing but the digital switches. So this is one position. What is another position? The switch may be connected to a ground. That means the switch will also connect to the ground. So this is the switch. These are the switches that we are going to design, right? Let us say this is my first bit, LSB, and this is my second bit in the 3-bit data design, 3-bit DAC, and this is my MSB, right? So here we can define the weight of this resistance. The weight of the MSB resistor is going to be 2 power 0, and this will be 2 power 1, and the weight of this resistance is going to be 2 power 2. So this is nothing but a weighted resistor network, and we are going to get the final output from the feedback resistor, which is called as RF. And let us say all these are the values. What is the value of these resistors? 2 power 2R, this is going to be 2 power 1R, and this is going to be the 2 power 0R. and these are the corresponding bits. So what is my data now? B0, B1 and B2. Here we define or we represent B2 as MSB and B0 as LSB, right? Always remember, in the weighted resistor network, the MSB bit, the weight of the resistance corresponding to the MSB bit will be very, very small compared to the remaining bits, and this resistance will decrease of the order 2 to the power, right? So in this B0, what is the resistance for B0? B0 is going to have a resistance of 2 power 2R. The resistance for B1 is going to be 2 power 1 into R, and B3, the MSB bit, which is B3, or sorry, B2. It is not B3, it is B2. Since it is a 3-bit operation, the bits are represented as B0, B1 and B2. Where B0 is an LSB, the corresponding resistance is defined as 2 power 2 into R. So usually we express it in terms of the ohms. So this is the resistance, and this is the weight of the resistance for the bit B1. So number of ohms, and finally the MSB expressed as B2, defined as B2. The weight of this resistance is going to be 2 to the power of 0 R. This is going to be 2 power 0 into R of ohms, right? These are the binary data and corresponding weights of the resistance, and finally here we are going to get the output, right? Now let us analyze this weighted resistor network. So the name of this network is called a weighted resistor DAC. It is obtained because of this configuration. This looks like a weighted resistor network where the resistance of the network is not uniform. The resistance of the network is not same. It is varying according to the bit position. According to the bit position, the weight of the resistance is going to vary. So LSB is going to possess the highest amount of resistance, and MSB is going to possess the least weight. The weight of this MSB is going to be very, very small. The resistance weight is going to be very, very small. Now we said these are the digital switches. We define these things as a digital switch, right? On what condition the switch will toggle, right? Let us say the bit binary. So what is the switch position for the data 1, 0, 1? For the switch position 1, 0, 1, what is the for the data 1, 0, 1, what is the switch position? What is the position of these switches? So what is the B0? The incoming bit B0 is binary 1. So the switch will be connected to the reference voltage, and we said B1 is going to be 0. The second bit is going to be binary 0. So the position of this switch B1 is connected to ground, whereas the MSB bit B2 is going to be binary 1. So the switch is once again connected to the reference voltage. So the digital switch will take two positions. So what are they? The position may be ground, or it can be the reference voltage minus VR. So on what conditions the switch will be connected to the ground? If the incoming bit is 0, for binary 0. For binary 1, the bit will be connected to the switch will be connected to the reference voltage for the incoming binary 1, right? This is the design. So here we are going to say this is nothing but IC741 itself can be considered to design your DAC, right? So now let us analyze the circuit here. So this is what is defined: MSB, LSB, considering a 3-bit data, right? Now here I am going to perform a nodal analysis. So these are the corresponding expressions you will notice. So what is my output? Output is going to be the V0. So which is defined as minus V0 by RF. Since it is, I am going to perform a nodal analysis. Output current, let us say. The output current I0 is defined as V0 by RF. So it should be the plus. Okay, let it be V0 by RF. And so let us say the bits are going to be B0, B1 and B2. Okay. And we said B0 is LSB and B2 is MSB. If you apply the perform the nodal analysis, we are going to get, let us say, if the switch is connected to the ground. If the switch is connected to the ground, so what is the nature of the signal? It is going to be 0, right? If the switch is connected to the reference voltage, so it is going to be VR into, let us say, the MSB bit B2 divided by, what is the corresponding resistance? We said it is going to be 2 power 0 into R. This is for the switch B2. And we have the second switch. What is the second switch? That is connected for the binary data B1. So once again, if the switch is connected to 0, we are going to get the third term. So what is the third term? If the switch is connected to 0, it will be 0. If it is connected to the reference voltage, we are going to have VR into B1 divided by, what is the weight of the resistance? The weight of the resistance is going to be 2 power 1 into R. This will be the second term for the second bit. And coming to the LSB. What is our LSB B0? Once again, the switch will take two positions. Let us say, if it is connected to 0, that is ground. If the switch is connected to the ground, corresponding signal will be 0, plus if it is connected to reference voltage, we are going to have VR into B0, and the weight of this is going to be 2 power 2 into R, right? So on LHS, we are going to have three terms, that is the sum of these three terms, which leads to the output called V0 by RF. So this is what we are going to get, right? Now, from all these expressions, so this is what we are going to get after simplifying the equation, simplifying LHS and RHS. So let us represent LHS as V0 by RF and RHS as the three terms, right? So in all these three terms, if we observe, we have some common terms. What are they? The common terms are going to be VR by R. So let us take VR by R as a common. So what we can get? And also, if we perform cross multiplication, let us bring this denominator RF to the opposite side. So you are going to get the expression. We are going to define this expression as like this. So it is going to become VR into RF divided by R, and here we are going to have the three terms. What are the three terms left over here? Are going to be B2 by 2 power 0 plus B1 by 2 power 1 plus B0 by 2 power 2. So this is what we have. The same thing is represented. Now, what are RF and R? What is the nature of RF and R? Both represents resistance. Both are going to be the resistance with some ohms, right? So where RF and R are nothing but resistors with few ohms of resistance. So for instance, if we assume the values of these two resistance, so where RF is the feedback resistance in the circuit, so this is RF, and R is the weighted resistance. Let us say RF equals to R. For the simplification of this, for simplifying this, we are going to assume both RF equal to, if I say R equal to 2RF, or even we can say R equal to RF. So let us consider R equal to 2RF. Now what will happen to the expression? You are going to rewrite this R by means of 2RF. right? Now we can cancel out both the numerator and the denominator RF. So what we have now, the leftover equation is going to be this, that is the output voltage due to the processing of 3-bit data B0, B1, B2 is going to be VR by 2, B2 by 2 power 0, B1 by 2 power 1 and B0 by 2 power 2. This will give you some magnitude, some volts, right? So where VR is, what is VR now? VR is nothing but the reference voltage. Understand? This is for a 3-bit data. So what happens if we consider an n-bit data starting from 0? Let us consider the bit sequence is going to start from 0 up to n-1. This will be considered as an n-bit data. Right, now let us generalize the obtained expression for 3-bit data. This is for 3-bit data operation, 3-bit data conversion. This is for 3-bit data conversion, right? That leads to produce and corresponding output voltage of V0. So if we want to generalize it, it is going to be very simple. So what is B0? So we need to remember the bit positions. So which is LSB and which is MSB. So in the very beginning of the analysis, we define B0 as LSB and B2 as MSB. Corresponding to the corresponding weight of the resistance is defined as 2 power 0. Always remember, the MSB bit is going to possess a least amount of resistance compared to the remaining bits. So what is my MSB? If I say n-bit data, so 0 is going, the first bit is going to be LSB and n-1th bit is going to be MSB. This is going to be an MSB, right? So if we replace it, the positions of MSB and LSB, so what is going to happen? Now B0 will be the LSB and Bn-1 is going to be the MSB. B0 as LSB and Bn-1 is defined as or represented as MSB. So now we are going to get the generalized expression, that is Bn-1 by 2 power 0 plus Bn-2 by 2 power 1 plus so on up to B0 by 2 power n-1. So this is a generalized expression for the weighted resistor DAC, right? Now, so this is the relation between digital input and analog output. The output obtained in this design is, in this converter is going to be the analog output for a given digital data. Since we consider this as a 3-bit data operation, the 3-bit operation do possess, there are 8 number of possibilities. What are they? 1, 2, 3, 4, 5, 6, 7, 8. Always in digital data representation, we start with 0. So it can be 0, 0, 0, 0, 1 and it is going to be 0, 1, 0 like this up to the 7th one is going to be 111, right? So if this is the data, which is going to be the, if this is the data, that means all the 3 bits, if all the 3 incoming bits are at 0, 0, 0. So this is what the corresponding analog output, right? And we'll go up to 1/8 of this voltage because we have 8 different positions, 8 different values, 8 different data types are going to obtain, right? And finally, here we can get the voltage which is going to be the 7/8 voltage, right? 7/8 of this voltage. This is just a comparison or relation between the obtained output voltage, obtained analog outputs for different digital data. This is just a comparison. So what we are going to say, these are the variations of the voltages that one can obtain for designing or for weighted resistor DAC, right? Now coming to the advantages and disadvantages. So let us go back to the design. So what we are going to design, this is going to be a weighted resistor network. So here comes the major issue. So what is it? The design consists of multiple values of resistors. The design consists of multiple values of resistors, which is a challenging task. Is going to be the major drawback of this design. So let us talk about the drawbacks. The binary weighted resistor DAC are as follows. So what are the first one? The difference between the resistance values for LSB and MSB is very large. Let us say for 3-bit data, one resistance is going to be 2 power 0 into R, and other resistance is going to be 2 power 2 into R. So what is this one? R, and this is going to be 4R. If I say the value of our resistance R equal to 1 kilo ohm, what is the value here? I need 1 kilo ohm resistance for MSB and I need 4 kilo ohm resistance for MSB. This is for 3-bit, right? If we say 4-bit, what is the difference here? 2 power 0 into R for MSB. The weight of the resistance for MSB is going to be 2 power 0 R. For LSB, it is going to be 2 power 3 R. So what is the resistance here? If I consider still 1 kilo ohm, so it is going to be 1 kilo ohm. And what about the LSB? LSB is going to have 8 kilo ohm resistance. So this is just for a 4-bit operation. Imagine we are going to work with 8-bit data, 16-bit data, 32-bit data, or it can be a 64-bit data, 128-bit data. Now what is the difference? If you say 16-bit data operation, MSB is going to have the same resistance 2 power 0 R, whereas LSB is going to have 2 power 15 times of that of the MSB resistance. So this is what the major drawback. The difference between the resistance values between LSB and MSB is very huge, right? And the another challenging task is this. It is difficult to design more accurate resistors as the number of bits present in the digital data increase, right? So because we are going to use multiple resistors, it is not 1 or 2 or 3. So if you are aiming for a 16-bit data operation, we are going to design 16 number of resistors. We are going to design, or we are going to use 16 numbers. All are different. If you see it is going to be a 32-bit data operation, we need to design at least 32 number of resistors very accurately with high precision. And no two resistors are going to have the same value. They are going to have the different values. This is a challenging task. Designing multiple resistors with multiple or different values is a challenging, right? And then definitely, so what is another drawback here? We need a wide range of resistors. So I'm not going to design the circuit saying the maximum resistance is going to be 10 kilo ohms. Or am I going to design my circuit with maximum resistance of 100 kilo ohms? No. The wide ranges of multiple resistors are needed, right? So it may lead to 1 mega ohm, 2 mega ohms or 100 mega ohms. The values of these resistors are going to be the challenging in the design once again, right? So what we are going to say, the number of binary input increases, it is not easy to maintain the resistance ratio also. So here in the output, if you remember, we are going to have the resistance ratio. What is it? RF by R. So it is very difficult to maintain this resistance ratio consistently for all the bits, for all the binary data. For simple or for 3-bit data or 4-bit data, one can maintain easily. As the number of bits, as the number of digital data with high number of bits, 4-bit, 8-bit, 16-bit, this is going to be another challenging task, right? So these are the major drawbacks of this weighted resistor DAC. So once again we look at this drawbacks, because we are going to overcome these drawbacks in the upcoming lecture. So that is going to be the R2R ladder network. So we are going to design an R2R ladder network or R2R ladder DAC, right? So there we are going to design the DAC with the help of only 2 resistors. So let us quickly look at all these drawbacks. It is all about the resistors. The resistor values considered here are not consistent, and moreover we need wide range of resistors, and the values are going to be increased. The values of the resistors are going to increase as the number of bits increase. For 3-bit data, 4-bit, 8-bit, it can be tolerable. So what happens if I am going to design a DAC for a 32-bit DAC? If I want to design for 32-bit DAC using this weighted resistor design, this is a very challenging task, right? So these are the major issues with this design. So what are they? The difference between the resistance values is huge. If you consider an LSB and MSB, and it is very difficult to design such a accurate resistors, such an accurate multiple resistors, and the range of these resistors are going to be huge, right? And final one, when number of binary bits increase, right, the resistance ratio, so that do considered in the analysis, the resistance ratio we consider is going to be very challenging to maintain consistently, right? So in the next lecture we are going to discuss the R2R ladder network to design digital to analog converter. That we will see in the next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.